We begin now the second part of the course. In the first part, we have talked about reactive control, covering this specific control framework called task space inverse dynamics. And in the second half of the course, instead, we will talk about trajectory optimization. In particular, I want you to think of the following question. In task space inverse dynamics, we have always started from the assumption that we had some reference trajectory to track. So for the manipulator, it was first a joint space trajectory, then we moved it to an end effector trajectory, which is a bit easier to get because we could just design it by hand. And then when we moved to the legged robot, we started talking about reference center of mass trajectory. Especially we have used sinusoidal motion for the exercise 2, and we were moving the reference trajectory by hand with the GUI in exercise 3. But now if we think of more complex scenario where we don't want to just play a bit with the robot to make it move, but we want to make the robot walk, for instance, then coming up with a reference trajectory for the center of mass and the feet and the posture, designing it by hand, well, we can immediately see that is not a trivial task. So to get reference trajectories in these non-trivial cases, one tool that is very common to use is trajectory optimization, or sometimes I will refer to it as optimal control, even if, to be precise, they're not exactly the same thing. Do you know what the difference is between trajectory optimization and optimal control? Come on, you've taken the class with Professor Biral, with Enrico. You should know. Take a guess, just by the name. Trajectory optimization, optimal control. Which?
Not control, you have to control signal in the trajectory, not.
Yeah, okay, that could be a good explanation.
You have a set point in the trajectory.
Yeah, in trajectory optimization, you may not have the control signal. You may just have a trajectory to optimize. That's true. But let's suppose that you're doing trajectory optimization and you're in one of those cases where you also have the control signal. So I'm not sure if this is official, but my explanation of the difference between the two terminologies is that when you're doing optimal control, you're looking for a control policy, which is not just a trajectory, but it's a function that maps the state to the control, so that you know what to do no matter where you are in your state space. Whereas when you're doing trajectory optimization, you're finding an open loop control, basically. So you find a mapping from time to control signal, not from state to control signal. Okay, that's the key difference. So for instance, when you're doing LQR, that is optimal control, because LQR gives you a mapping from the state to the control. Whereas when you're doing collocation, which you might have seen with Enrico or Francesco, have you? Collocation? No? Okay, well, we're going to talk about that. Then you're doing trajectory optimization because you're just getting an open loop trajectory that you can take and execute, and it will never work on a real system. Okay.
And we used to call optimal control also what you just called the trajectory optimization.
Yeah, I will do the same.
Yeah, because but we solved the problem with the time, and that's it. We get an open loop.
Yeah, I know everybody does the same, but just before becoming sloppy, I wanted to be a bit more precise and tell you, in theory, there is a difference between these two methodologies. In practice, very often these two terms, they are confused and people talk about one or the other independently. Okay.
Did you say that the optimal control has the knowledge of the dynamics?
No, because also in trajectory optimization, you typically have the dynamics as a constraint.
Okay.
So the trajectory you get satisfies the dynamics, typically. What you don't get is a control policy. So typically what people do is that they do trajectory optimization to get a reference trajectory, and then they use it as a reference for a controller to track. And that's exactly also what we're gonna do. Okay, so we're gonna talk more about this later.
So also MPC is trajectory optimization doing linear recursive fashion, because you do not have a true loop close. You do not have a control policy. You get from inverse dynamics the control signal.
Yeah, you can see MPC as trajectory optimization recursively iterated, or you could see it as the online computation of a control policy, because the control you get at each time step depends on the state, because you re-solve the whole optimization problem with the new initial state, which is your current estimation.
Okay.
Yeah, I mean that's just point of view.
If you consider it as a closed loop or an open loop.
Yeah, but the problem you solve is open loop,
Yeah.
so there is no discussion about that. There are other kinds of MPC, such as robust MPC or stochastic MPC, in which you really optimize for a control policy. Because when you start taking into account uncertainties, then you can no longer do an open loop integration. You need to have some kind of feedback. But in the classic MPC, you're correct. It's an open loop optimization problem. Okay, so we will start today by looking at what are the limits of instantaneous control, which is going to give us some motivation to look into trajectory optimization. And then we're going to discuss this very specific model that is used for walking robots, which is basically needed if you want to apply trajectory optimization in a fast way. Because applying trajectory optimization for the complete dynamical model of a walking robot, we will see that is very, very difficult and computationally demanding. So very few people do that. Most people use simplified model, and especially this is the most common one, so we're gonna go through it. And then we're gonna see how we can use this simplified model to do trajectory optimization for the center of mass of the robot to get a desired center of mass trajectory. We could also do, with a slight modification to this optimization problem, we can also optimize for the footstep positions of the robot. And we will probably next time use an existing Python library that's been implemented by a PhD student I am co-supervising at the Max Planck Institute in Tübingen to generate a center of mass trajectory. And finally, hopefully on Friday, we will connect this center of mass trajectory with the TSID controller to generate a complete walking motion in simulation for the humanoid robot Romeo. Actually, you should have already seen the motion, because that's a script that I suggested you to run to test the virtual box on the first day. Is exercise 4. And then we can play a bit with the script, changing the number of footsteps, the length of the steps, the speeds of the walking motion, and see when it works, when it doesn't, why it doesn't, this kind of stuff. So let's start by talking a bit about the limitation of reactive control. So reactive control is very good if you have a reference trajectory that you know it's feasible or almost feasible for the system, and you want to track it, such as what we did so far in class. But the problem of it well, apart from it doesn't give you the reference trajectory, you need to get it somewhere else. But even assuming you have the reference trajectory, the problem of reactive control, as we saw it here, is that it has no notion of the future state of the robot. So everything you can express must be a function of the current state and the current control of the system. And that's the main difference between reactive control and optimal control, right? In optimal control, you have a preview of what's going to happen. You have a representation of the state and control trajectory of the future. In reactive control, you don't. So the key problem when you don't is that it's very hard to anticipate the potential violations of the constraint in the future. So we saw that in reactive control, we can account for some constraints. We had the friction constraints, no problem with that, because those are related to contact forces, and contact forces are your control inputs. Basically, they are affine to your control inputs. But when it comes to other kind of constraints, such as the joint position bounds, for instance, which we mentioned but we didn't really test in the script, those are quite hard to capture with reactive control, because joint positions, they are not one of the variables of your problem. The variables of your problem are the joint torques, the contact forces, and the joint accelerations. So how can you express a constraint on your positions? Well, we saw that there is a trick that we can apply. We can say that my future position is the integration basically of my current acceleration over one time step, and then I can express the constraint on my future position. But even if you do so, it's not going to work very well. And I'm going to try to explain you why with a simple example. Think of a car that is moving towards a wall. Okay, so this is the wall, this is the car, and the car moves. So you are the controller. You only know the position and the velocity of the car right now, and you can decide the acceleration. And you have this constraint in your optimization problem formulation that tells you the next position shouldn't be beyond the wall. Okay, so you keep accelerating, and so far everything is fine. You integrate one time step, so far everything is fine. You keep accelerating, so far everything is fine. When you're at 1 centimeter from the wall and you're running at 100 kilometers per hour, well, there is no problem. Everything is fine. And then at a certain point, you realize that, well, if I keep moving at this velocity, I will violate the constraint. But by the time you realize it, it's too late, because you don't have the deceleration capabilities to stop at this point. Okay. So that is why reactive control is not sufficient by itself. You need somehow a preview of the future to foresee potential problem and act now to prevent them from happening. Okay, this is exactly why people look into optimal control and they're not happy only with reactive control in general. So you can think of trajectory optimization as basically an extension of task space inverse dynamics with a preview horizon. You just apply the same methodology, but having a preview horizon into the future of what's going to happen, so that you can incorporate constraints not only related to the right now or the next time step, but that also span the future several seconds forward in time. What is the problem with trajectory optimization? Well, the main issue is that it's just much more computationally expensive. So we saw that we can solve the TSID optimization problem in less than 1 millisecond. So we can execute it really, really fast in a real-time control loop on real hardware. forget you can do that with optimal control for a humanoid. So for a humanoid, you have 30 degrees of freedom, and if you think that you want to have, I don't know, a 2-second preview horizon discretized at 1 millisecond, which was the control frequency we were using with TSID, you're going to have 2,000 points in time times the dimension of the state, which is 30. That makes 60,000 variables. That's for the control. Then you typically have also the position and the velocity, so you multiply times 3, you get 180,000 variables. You cannot solve an optimization problem with 180,000 variables in 1 millisecond, not even in 10 milliseconds or in 100 milliseconds. I mean, it's going to take probably minutes to solve. So that's why we used reactive control in control loops, because trajectory optimization is too slow for reactive control loops. Otherwise, we would use it if it was sufficiently fast, because it's better. Okay. So what is the solution? The solution is, let's try to use trajectory optimization offline, so before executing the motion, to compute a reference trajectory that is feasible, satisfies the constraint, and that is smart because it foresees potential problems that may happen into the future. Again, my computer thinks I want to read email. I don't know why. And then once we have this reference trajectory, then we try to track it with the reactive controller. So at this point, the task of the controller is much simpler because it already has a reference that is feasible and that satisfies all the constraints right now and throughout the whole horizon. So it just needs to regulate basically the behavior of the system around this trajectory. So it's only a matter of local stability. It's no longer a matter of global stability and feasibility. And hopefully, if the reference trajectory we have computed is sufficiently far from the feasibility boundaries of the system, well, the controller is going to be able to track it even though we have some disturbances. Okay, so that's the idea. So we have somehow simplified the problem because we won't be trying to solve trajectory optimization online, we just solve it offline. So even if it takes a few seconds or a few minutes, it's fine. The problem is that when you're dealing with legged robots, or even when you're dealing with manipulation problem, because the two are quite similar, for a certain reason I will explain you, even solving it offline is super challenging. And the number one reason why it's challenging, can you guess? Let's say there are two main reasons why these problems are challenging.
I looked at the slides, so I cannot.
So, how big is the state of a humanoid robot?
The number of states are very huge in respect.
Yeah. So first of all, you have a high dimensional state because you have about 30 degrees of freedom for a humanoid.
And maybe I think you can have a more solution.
You mean, okay, you don't have a unique solution to the problem.
And this is for optimal.
That's more of a theoretical problem than a practical one. In practice, typically you add some regularization to your solver and you always have a unique solution, as we were doing with TSID. But if you're doing more theoretical proof, that's a problem. It's not our case here. But the dimensionality, it's a problem because, I mean, just a few minutes ago I was doing some computation to guess the size of the problem you will need to solve. The size is that big because you have a high dimensional state. And of course the size is related to the computation time. But size is not the only one. It's not the only thing that matters, as everybody knows in this room, right? There are other things.
Is it still convex? Yeah.
So the problem is not convex, most probably, unless you have a linear dynamics. Your problem is not going to be convex, and well, for manipulators or let's say multi-body systems in general, the dynamics is nonlinear, so the problem is not convex. That is a problem, but again, it's not the hardest problem, because for a manipulator, moving in space, you can do trajectory optimization without too many issues in practice. You have no guarantees, but in practice it works well. What's really peculiar of locomotion and manipulation is that you have contacts. You have typically rigid contacts. Again, not infinitely rigid in practice, but sufficiently stiff that it makes sense to model them as infinitely rigid in modeling. Okay. So if you go for the option of modeling contact as rigid, what you get is a hybrid dynamical system. And you know they are not easy systems to deal with. So if you just model it as a hybrid dynamical system and you try to write down the optimal control problem, what you get is a non-smooth optimization problem, because your dynamics basically jumps when you make a contact or when you break a contact. You have a jump in the dynamic equation, and so at that point basically Jacobians and gradients are not defined, and what's even more important, the numerical behavior of the solver is gonna be really bad. So it's gonna have problems converging, it's gonna converge really, really slowly, or it's not gonna converge at all. So that's typically not the way to go. The other option is to say, well, but my contact has some softness, even though the stiffness of the contact is high. So I can model them as soft contact. So the more I penetrate into the material, the higher the reaction force I get. You can do that, but since the contacts are stiff, you're gonna get stiff differential equation representing your dynamics. Stiff when it's related to differential equation, it means that they are numerically ill-conditioned. Okay. So your numerical integrator is going to have lots of problem integrating a stiff differential equation. It's going to be very, very slow. That's what stiff means in this context. And so the optimal control problem is going to be very slow to solve. So in neither of these cases, you're going to end up with something that you can really use in practice. So the solution that works the best, let's say nowadays in robotics, is to do like that. We use rigid contacts for modeling, but we don't want a hybrid dynamical system. So what we do is that we fix a priori the contact sequence. So we decide, we meaning the user, decides beforehand what is the sequence of contacts that the robot should make. And if you think of a biped locomoting, well, that's an easy guess, right? You start on both your feet, then you go on your left, then you go again on both feet, then you go on your right, then again you go on both feet, and you keep iterating. Left, double, right, double, left, double, right, double. That's a cyclic pattern. So for certain cases, it's very easy. If you think of a quadruped, it's less trivial because you have many different gaits. You have the crawl, you have the trot, you have the bound, And probably Michele can name another 2 or 3 gates that you might have with a quadruped, but I mean, you have many different combinations. And if you also use our imagination to think of cases that go beyond the walking on flat ground, if we think of uneven terrain, if we think of climbing, if we think of, I don't know, just doing these kind of things, you have infinitely many options when it comes to the choice of which contacts you can make. Okay, but if we start from the assumption that we can decide beforehand the contact sequence, then the problem becomes immediately much, much easier mathematically. Because if we know which contacts we are going to make and when we are going to make them, then the system is no longer hybrid. It's just time varying. So my dynamics changes depending on which contacts I have. Okay, but since I know this beforehand, it's not a hybrid system. The hybrid system is when you have a jump that depends on your state, but here you have jumps that depends on the time. And it turns out that mathematically, for an optimal control solver, that's much easier to deal with. Okay. So not everybody is doing this in robotics. There are some people that are trying to go this way or this way, but they're just much more difficult. Whereas this one, it works out of the box. So this is the one we're going to use. Question? Again, reading my email. Okay, as I said before, there is another problem, which is the dimensionality. And this is what really motivates us to look at a simplified model. So instead of optimizing for the complete motion of the system, which is in a 30-dimensional space, more or less, we're going to use a simplified model that captures, let's say, the dominant dynamics of the system. And then we're going to use a controller to map from these dominant dynamics, which is going to be the center of mass for walking, to the complete state, which are the joint torques, basically. And that's going to be TSID. The other good reason for using simplified model is that if the model is simple enough, so it's small dimensional, and it is linear or quasi-linear, then we can even hope to solve this kind of problem online, and then we can use it in an MPC fashion. So by resolving the optimal control problem at every control loop, which of course is going to make the whole controller much more robust, because we can not only change the joint torques, keeping the same reference center of mass, but we can also adapt the center of mass reference trajectory according to the perturbations that I get on my system. If you think of a humanoid walking again, I can plan for a desired walking motion, like, I don't know, 3 steps forward, 1, 2, 3, and that is fine, but I can only track this if nobody pushes me. Because if when I'm here I get pushed, I will need to step to the side to recover. If I keep trying to track the nominal center of mass, I will fall. Okay, so having the optimal control solver inside the loop is of course a good thing, but I can only hope to do that if I have a sufficiently simple optimal control problem to solve. And using a simplified model, well, it's going to make it sufficiently simple in practice. So we're not going to actually do anything related to MPC in the scripts. We're just going to stick to the optimize offline and then track online. But just you should know that the kind of optimal control problems that we are solving, they are sufficiently simple that people have really implemented them in an MPC fashion. So there are different kinds of reduced models, simplified models, that are used for locomotion. One is inverted pendulum, so you just assume that your robot is an inverted pendulum. And the center of mass is located basically at the tip of the stick. And the stick is massless, so you just have one single mass at the top. The problem with the inverted pendulum is that it's nonlinear, because you have, of course, a cosine for the gravity term appearing. So an even simpler model is the linear inverted pendulum, where you assume that the motion of the system is going to stay on a line. So it's like an inverted pendulum, but you can imagine that you have also a prismatic joint on the stick. So as the pendulum falls, the stick gets longer and longer, so that the tip of the stick remains on a straight line. Okay, that's a linear inverted pendulum. That's the one we're going to use, and the main advantage is that it's linear. And then you have a slightly more advanced model, which is the so-called centroidal dynamics, which basically means that you're modeling the whole robot as a single rigid body. It could be a point mass, or it could also have an inertia. It doesn't change much. And you say, well, for trajectory optimization, I assume my whole system is a single rigid body. The main disadvantage of this is that it's nonlinear. Again, we're going to see why in a moment. So we're going to actually start by writing down the dynamics of a single rigid body. And then we're going to see that under some assumptions which are reasonable in the case we are going to look at, we can translate this nonlinear dynamics into the one of the linear inverted pendulum, so that we get a better feeling of in which situation this model is valid, and you can hope to use it for trajectory optimization. So I need to go 5 minutes to the whiteboard for this. Can you survive to that? Great. So first of all, let's start from the dynamics equation of a single rigid body. For the translational motion, you have that the mass times the acceleration of the center of mass plus gravity is equal to the sum of the external forces, right? And you can imagine you have an arbitrary number of external forces. It doesn't matter. That's the equation. So that's Newton equation. Then for the angular motion of the system, you have the Euler equation that says that the rate of change of the angular momentum is equal to the sum of the moments. But since I only have contact forces applied to the system, the moments are just the cross product of the lever arm times the contact forces. So P is the position of the contact point, and C is the center of mass. L was the angular momentum, M the mass, G gravity, F contact force. I guess this is quite standard notation, so you should be familiar with most of the terms. Now, why is this dynamics nonlinear? Well, first of all, let's start from the very beginning. What's the state of this system? So every dynamical system has a state and a control input, right? So before we start working with the system, we should know what's the state and what are the control inputs.
Positions and velocities for the states.
Of? Position and velocity of?
Center of mass.
Okay, position and velocity of center of mass. And if we also consider the angular part, we have also the angular momentum inside the state. we would have also the orientation of the body inside the state, which doesn't appear here, but it's a part of the state for a single rigid body. Okay, that's a state. What are the control inputs?
Acceleration.
Not really.
Contact forces.
Yeah. The forces are the control inputs in this model. And the accelerations are a result of the contact forces. It's similar to what we had with task space inverse dynamics. The control inputs were the joint torques, and then the joint accelerations were a result of these torques. Okay.
Cannot we do the same approach of before and removing the forces and using acceleration directly as inputs and then get back the forces converting? Is it possible?
Let's try to simplify. No, I forgot. Why is that nonlinear? Now that we know what the state is and what the control is, why is that equation nonlinear? What's the term that makes it nonlinear?
Vector product.
Did you cheat or?
No, because yes, they are combined basically.
Also the
forces and
gravity,
states.
but it makes it affine or something.
Yeah. By linear I mean affine.
Okay.
Affine is fine.
Yeah, so the vector product.
Yeah, because you have the cross product between C and F. So you have a multiplication between your state and your control inputs. So X multiplies U using the standard notation of dynamical systems. So that's nonlinear. And nonlinear, of course, means that your optimal control problem is going to be non-convex, which is never a nice thing. So ideally, we would like to make this linear. And the good news is that under some reasonable assumptions, we can do it. And I will try to show you how. So actually, the first equation is already linear, right? MC double dot plus G equals sum of F. That's linear. I have no multiplication between state and control. Actually, the state doesn't even appear in that equation. So the problem comes from the second equation, the Euler equation. So let's write that equation down. But instead of writing it as a three-dimensional equation, I will write down the single scalar equations, focusing on the x and y component. Okay. So we have L dot x. Okay, this doesn't write very well. Okay, this is better. Is equal to the sum over I of Piy minus Cy Fiz minus Piz minus Cz Fiy. So since we work a lot with this equation, I learned by heart the cross product. If you were wondering how I knew it, it's because we use it a lot. So that's the first line, and the second line is similar. I got L dot y is equal to the summation over I of Pi z minus Cz Fix minus Pix minus Cx Fiz. Okay. So we can immediately see the source of the problem, which is here we have this product, here, here, and here. Okay, this is where the nonlinearity is coming from these products. So what we typically do in leg locomotion is that when we are walking on a flat ground, which is what happens for most of the time, we can assume that the center of mass height is going to remain constant. That's a very reasonable assumption. So even when humans walk, center of mass height is not exactly constant. There is a bit of movement, but it doesn't move much. So we will take the following assumption. First assumption, we are walking on a flat ground. What does it mean in terms of math? That the height of my contact point, PIZ, is going to be the same. It's going to be constant, the same for all the contact points, because Z is aligned with gravity. So flat ground, it means the same Z. And since it's the same for everything, and I can put my reference frame wherever I want, well, I will put my reference frame on the ground so that PIZ is 0. For all I. So this means flat ground. And then the second assumption is that since I'm walking on a flat ground, also the height of my center of mass is going to be constant. So C double dot Z is going to be equal to C dot Z, which is going to be equal to 0. Okay. Third assumption, which is actually not really needed for making the equations linear, but it's typically taken anyway, is that my angular momentum is going to stay at 0. Which means basically I'm not going to have fast movement, angular movement of my trunk and my chest and my waist. Which again, for a human walking, it has been shown that it is typically the case. The angular momentum is kept very small during locomotion. Of course, if you want to do a backflip, no. But for standard locomotion, it is. So, exploiting these 3 reasonable assumptions for the context we are discussing, we can show that this equation here will become linear. How? Well, let me start. I will move the, so this is 0, this is 0. This is also 0. So this is 0, this is 0, this is 0, and this is 0. We have already simplified a few things. Now I can move the terms depending on the center of mass to the left. So I get here Cy times summation of Fiz minus minus plus, then here it becomes again a minus, minus Cz summation of Fiy is equal to summation of Piy Fiz. That's the first equation. And the second is Cz times summation of Fix. Minus and minus becomes a plus, then it becomes a minus again, minus Cx summation of Fiz, which is equal to minus summation of pi x fi z. Okay. Nothing special, I just moved things around a little bit. And now what I can do is that I can exploit the first equation, the Newton equation, to see that all these terms here, the summation of the forces over z, summation of the forces over y and over x, I can rewrite them as mc double dot plus g, right? Knowing that g is just appearing in z, not in x and y. Okay. So I have let me also do another thing, since I'm here. I will divide everything times the summation of the forces over z. So here, this goes away, and here. Okay. If I move here, what I have is cy minus cz times the summation of the forces over y, which is mc double dot y. I have no gravity in the y direction. And here are the summation of the forces over z, which is mc double dot z is 0. That was one of the assumptions. So I just get mg. And that is equal to the summation of pi y fi z over the summation of the forces over z. And here, similarly, I multiply, or I don't. No, yeah, I multiply everything times -1 to make this positive. So I get cx minus cz. The summation of forces over x is mc double dot x. And the summation over z is mg, because I have no acceleration of the center of mass over z. And that is equal to the summation of the contact point x times fiz over summation fiz. And I have a small simplification here, because the mass can remove it. Okay. So, first observation. Is this dynamics linear?
No, it's not. There is C times C double dot.
Okay, but is it linear under the assumption
No, there is
that Cz is constant? So since Cz is constant, I can remove it from my state. It's just a constant, it's no longer a state variable. So even if here I have indeed a multiplication between state and its derivative, this is no longer part of the state because it's constant by assumption. So I can see Cz over G as just a constant, a parameter of my dynamics. So my state is really Cy and the derivative of my state is c double dot y. So this is linear, and here I have a problem, actually, because here I have the ratio between control inputs. But the good news is that if you think about what this really represents, here I have basically an average of the contact points weighted by the corresponding normal force that is applied at each contact point. Okay, so if you imagine that you have two contact points, one here and one here, if you have all the force here and 0 here, then this is going to be equal to this. If you're in the opposite case where you have 0 force here and all the force here, it's going to be here. And if you have equal forces at the 2 points, it's going to be right in the middle, right? Because it's a weighted average. So what is the physical meaning of this? Yeah, Gastone said it. Or Marco said it.
Center of pressure.
It's the center of pressure. Okay, that's a weighted average of the contact point weighted by the normal forces. That's exactly the definition of the center of pressure. Okay, so we can say that our new control variable is going to be called Z, which is the center of pressure. And the center of pressure, as long as my contact forces in the normal direction are positive, is going to stay so I have a weighted sum, a weighted average of the contact points where the weights are positive. So suppose these are my contact points, okay? They define a polytope, right? Any weighted average of points with positive weights must be inside the convex hull of the points. It cannot go outside. To go outside, I would need a negative weight, which corresponds to a negative normal force, which would be a force that pulls on the ground. But since I can only push, I'm going to stay inside, which is physically consistent. My center of pressure cannot go outside my contact surface. So just by saying that the center of pressure is staying inside the convex hull of the contact points, I am implying that my contact forces in the normal direction must be positive. So these two constraints are equivalent, are the same constraint but represented in different spaces. One is in the space of contact forces, the other one is in the space of the center of pressure. So I can stop using the contact forces as my control variable, because I can see here that the only thing that matters is not the single contact forces, but it's the global center of pressure. That is what defines my center of mass acceleration. Okay, so my new control variable is going to be the center of pressure, and by choosing the center of pressure, I can compute directly the center of mass acceleration in x and y direction. In Z, it's 0 by assumption. And these equations here are actually equivalent to the linearized equation of an inverted pendulum. But here, instead of deriving them from the inverted pendulum equation, we have derived them from the equation of a single rigid body, which I think is closer to the dynamics of a multi-body system. and we have seen under which assumptions these equations make sense, which are basically the assumption of walking on a flat ground with a constant center of mass height and with zero angular momentum. Questions?
So that equation represents a point that follow the center of pressure with a second order system.
So this is really the center of pressure, and the center of mass actually is pushed away. I will show you better last time, now it's late so I stop here, but this is an unstable dynamics, so the center of mass is pushed away from the center of pressure.
You're applying a moment in the other direction.
Yeah. So if you think about yourself standing, if you raise the tips of your foot, so you move the center of pressure back, then you're going to fall forward. But the center of mass is pushed away from the center of pressure. It's an unstable dynamics, that's why it's a bit tricky to control. Okay, so let's stop here for today, and next time on Wednesday we see how we can use these dynamics for doing optimal control.